Okay, so today we're actually going to start chapter 2, which we're going to talk about two pretty important topics, which has to do with tangent lines and velocity problems. However, today we're kind of going to talk about some indirect approaches to tangent and velocity problems, and then we're going to kind of define them more specifically later on in this chapter. So let's first start off by talking about the tangent problem. And so, which by the way, this is a very, very important concept. So what we care about is strictly working with tangents to curves, and more specifically, when we're working with these tangents to curves, we want to find the slope of the tangent line, and that's kind of going to play a very important role in calculus. So let's just quickly define what a tangent is. So a tangent to a curve is a line that intersects the curve at exactly one point. Okay, so what what we want to kind of think about is, so visually speaking, is think of it this way. If I have kind of like a curve that does this, okay, and if I draw a tangent to this curve through that point, the tangent line would look something like this. And let's call this line L. Now, if you look at this, you might say to yourself, wait a minute, how is this line a tangent to this curve? Because by definition, what are we saying? It's going to intersect the curve at exactly one point. So what we actually care about here is that if I kind of zoom in on this region right here and ignore everything else, notice how this line is in fact tangent to that curve at that point. So especially in calculus, we don't really care about what happens in the long run or the grand scheme of things. We only care about kind of like a small neighborhood of this point. So this line acts as a tangent in this region. So we don't really care to go too far out, just in the vicinity of this point, this line definitely acts as a tangent. So what we could say here is that L is a tangent to the curve. And why don't we kind of put into writing as to what I was talking about here? What we could say is, look, even though L intersects the curve at 2 points, we are concerned about the line being tangent to a curve at a neighborhood of a specified point. So once again, although we could extend this out and say, wait a minute, how could this be a tangent? It intersects it here and here. See, I don't care about how far out I am or if I'm really far away from this point. As long as I'm near this point, like this, let's say the small screen that I made here, in this region, notice how that line is tangent to that curve. So therefore, this line is considered a tangent to that curve. Okay, so what our goal is going to be is to find the equation of this line. Okay, and of course, the most important part of finding the equation of this line is to find the slope of that line. Because if you remember from algebra, obviously, to be able to find the equation of a line, what do I need? I need the point on the line and the slope of the line. Well, notice how since this line is tangent to that curve at that point, this point is also on that line. So all I really need is the slope of this line, and then I could write the equation of this line in point slope form. So let's look at our first example where we're going to do that. And for homework from section 1, you're mainly going to use this idea, okay? And like I said, we're going to come up with better ways of finding these slopes of the tangent, but this is kind of like an introductory section to finding slopes of tangent lines. So for example 1, we're going to find the equation of the tangent line to the parabola y equals to x squared at the point P, which has coordinates 1, 1. So basically, here's what's happening. Just visually speaking, we all know what the parabola y equals x squared looks like, which is something like that. And the point 1, 1 is right here. So my goal is to find the equation of this tangent line. Okay? So basically, in other words, what we're saying here is that, look, we have a point on the line, which the point we have is strictly 1, 1. Okay? So in other words, where we're really stuck with here is that to find the equation of the line, we need to find its slope. Okay, now here's where the problem comes about. To find the slope of this line, I need 2 points on that line. However, I can't find a second point on that line, or at least it's impossible. So here's what we're going to do. What we're going to do is, and this is where kind of like we're going to use this really cool idea where we kind of force out the slope of this line. So what I'm going to do, and I'll show you this visually, is, see, fortunately for us, we have this parabola, which is y equals x squared. So what I'm going to do is I have this point 1, 1. And what I'm going to do is I'm going to pick any random point on this parabola. So here we go. Let's call this x, y. And I'm going to find the slope of this line, which clearly you could see that the slope of this line is nowhere near the slope of that line. Okay, so let's actually do that. So to find this slope, and see, the reason why I want to use a point on this curve is because if you give me the x coordinate of any point on this curve, I could find the y coordinate simply by just plugging it into that. So for example, if x is -2, then y is 4. If x is -10, then y is 100, and so on. So any point on this parabola, I could find its coordinates just by using the equation of the parabola. So here's what we're going to do. And the formula that I'm going to write for finding the slope is I'm going to write all the possible slopes of, in fact, the secants here, right? Because what I have is this line goes through 2 points, which means this line right now is a secant. So here's what we're going to do. We're going to find the slope, and let me go on to the next page. So let's say, to finding the slope, here's what we're going to do. We are going to use the slope formula, which we've learned is y sub 2 minus y sub 1 over x sub 2 minus x sub 1. Okay, so here's what we have. We have already 1 point that we want to use, which is 1, 1. And the second point, is any point on the equation or the parabola, which is y equals to x squared. And by the way, I want to make sure that I use a single variable. So this one, I mean, there are no variables here. However, when we say any point on the equation y equals x squared, that's going to be of the form x comma y. However, I want to write this with as little variables as possible. So here's what I could do. Instead of y, I could replace y with x squared, because over here we're being told that y is the same thing as x squared. So basically this is going to turn into x comma x squared. Okay, so here's what I want to do. I want to find the slope of the secant going from 1 comma 1 to x comma x squared. Okay, so using the equation or the formula for the slope, we get m equals to y sub 2 minus y sub 1. So we could say, I don't know, let's call that y sub 2, let's call that y sub 1. So it would be x squared minus 1 all over, and then we could say x sub 2 minus x sub 1. So x sub 2 is x minus 1. Okay, so here's the thing. This is the slope of any secant line from 1, 1 to x comma x squared. So in other words, here's what we're doing, just to kind of visualize it. So I'm making this parabola a little larger, just so it's easier to follow. So here's 1, 1. Now look at what happens here. Let's say that this is any point which we're calling x comma x squared. So right now we have the slope of this line, which is a secant. Now, you might be wondering, well, I'm not even close to finding the slope of the tangent. Well, here's where things get really interesting. So to get the slope of, like, let's say this red line, here's what we're going to do. And this has an x value of 1. So here's the thing. What's the problem? Why can't I plug in 1 for x and say, look, well, if you want to find the slope of the tangent line, we need x equals 1. If I plug in 1 for x here, the problem is I get a 0 in the denominator, so I can't do that. So notice what happens now. What if I move my x value even closer to 1? What if, like, let's say I make this my new x value? What do you notice happens to the slope of your secant? The slope of your secant, which is this purple line right now, is still not close to the slope of the red line. But what do you notice? The purple line has a slope closer to the red line than the black line did. And by doing this, now look at what happens. What if I pick an x value that's even closer to 1? Like, let's say if I pick this x value and I have that point. And so notice how the blue line is actually closer to having the slope of the red line as the purple line. So as you could see, the pattern we're seeing here is that as x gets closer and closer to 1, x squared minus 1 over x minus 1 gets closer and closer to the slope of the red line. So we actually start getting an idea as to what the slope of the red line would be. However, we could also do better than that. We can say, look, this equation that I have, I want to get as close as I can to 1. Or what if I could somehow simplify this that would allow me to plug in x equals 1? And I'm sure most of you are probably looking at this and saying, yeah, actually, I could do something to simplify this out. So here's what we could do. We could say, look, if we take, so if we have, if m equals to x squared minus 1 over x minus 1, we could say, simplifying this, yields the following. And if you're looking at this, you'd say, okay, look, the way I could simplify this is I could take x squared minus 1 over x minus 1. That's the same thing as, you could factor the numerator as x minus 1 times x plus 1 all over x minus 1. And the good news is you notice that you could cancel out the x minus 1, which then gives us x plus 1. So what does this allow me to do? This now allows me to plug in 1 for x. And when you plug in 1 for x, see, and we know that we're not saying that this guy's all of a sudden defined at x equals 1, but we have an open point at x equals 1. But we could also see that, look, if we're getting close to x equals 1, this fraction here, or this ratio, actually gets closer and closer to the value of 2. So what we notice here is that, well, notice as x gets closer to 1, the slope approaches 2. Which, what does that mean? See, now let's stop here for a minute. Let's go back to this picture. What we noticed is that as x got closer, or as these points got closer to 1, the slopes of my tangents got closer to the slope, or I'm sorry, the slopes of my secants got closer to the slope of the tangent. And so this is the visual representation of what's happening here. So you could see that as x gets closer to 1, this gets closer to 2, which, what does that imply? That implies that the slope of the tangent line is 2. And that's basically the hard part. Once we have that, now we could easily write the equation of the tangent. Now remember, why do we waste our time finding the slope of this tangent? It's because we're trying to write the equation of the tangent. So since the slope is 2 and it goes through the point 1, comma 1, we could say the equation of my tangent line is y minus 1 equals to 2 times x minus 1. And there you have it. Okay? So that takes care of the first problem, which has to do with the tangents. Okay? And then the second example, which we'll get into, has to do with the velocity problem. Okay, so the velocity problem gives us this simple goal. So our goal will be to find instantaneous velocity. So if you think about it, instantaneous velocity is different than average velocity. So if you think back to the velocity problems you've worked with in this class or in classes prior to this, you know that the formula for velocity, or better yet, you've heard distance equals rate times time, which rate is what our velocity is. So you said, look, if you want me to find velocity, that's rate equals to distance divided by time, which this does not give us instantaneous velocity because there's a big difference. This gives us average velocity. So here's what I want to point out. Before we do an example, and this example is going to be very kind of similar to this picture, so I guess what I could do is I could first give you the example, and then we could talk about how we would find instantaneous velocity. Okay, so example 2 says, suppose that a ball is dropped from the top of a building 450 meters above the ground. So what we want to do is we want to find the velocity of the ball after 5 seconds. Okay, so here's what's happening. Visually speaking, think of it this way. We're on top of a building, right? And a ball is dropped from the top of a building. And what we're saying is 5 seconds later, let's pretend that the ball is there. So what I want to do is I want to find velocity at that instance. And see, here's where this problem is more interesting than the distance equals rate times times problem, or rate is distance over time, is because as this ball goes down, as time goes by, because gravity pulls this ball down, this ball is actually picking up speed. It's getting faster and faster and faster. So, for example, the speed at the ball at this point is faster than the speed at the ball at that point. Okay, so as time goes on, the ball picks up more and more speed. Okay, so it's what we're trying to do here is we're saying, look, at this time, what's the velocity of this ball? Okay, so here's what we could do. First of all, we need to come up with a formula that gives me the position of the ball at each given time. Okay, so the formula for the ball is actually the formula that Galileo used to describe the position of a ball t seconds after it's been let go from some height. So you don't have to memorize this formula. It's also a kind of like a known formula in physics, which is described as following: S of t equals to negative 4.9 t squared. So remember, you don't have to memorize this formula. If we're using it, I'll give it to you on the test, so don't worry about it. So S is the position at t. Now look, if t is 0, it has this, the position is 0 because it hasn't been dropped. So basically what we're saying is this position right there has S of 0 is 0. Okay, and then so the further it drops down, then it'll create some position, and we could find its distance is traveled. So here's what we know, like mentioned. So from algebra, we have the average velocity equals to the distance traveled divided by the time elapsed. So once again, keep in mind that, see, this is average velocity. How come? Because when you say this distance minus that distance, or this distance divided by the time elapsed, that gives you on average from here to here how fast the ball is moving on average. But as we know, as the further this ball moves down, its speed, or the speed, actually starts increasing. So it moves faster and faster and faster. So we're just averaging the velocity out in algebra 1, and we're saying from here to here on average it travels, for example, I don't know, 10 meters per second. Okay, but it doesn't mean that all the way through it's traveling 10 meters per second, because that makes no sense. Because once I let go of the ball, it's at 0, then it slowly starts gaining speed. So when we average it out, we're saying on average this whole way it's traveling 10 meters, but it's not exactly at every single point. Okay, so here's what we could do. We could say, look, and let's talk about this visually. See, here's what I could do. The goal here is to help me find instantaneous velocity, which, like, let's say this is the position of the ball at t equals 5 seconds. See, if I go far away from t equals 5, let's say the ball is here at t equals 4, and if I use the idea of distance traveled over time, would you think that this, if I take the average distance, or the distance traveled divided by the time, and I use the average velocity from here to here, do you think that would be a good approximation of the instantaneous velocity at 5 seconds? And the answer to that should be no, because look, from 4 to 5 seconds, the ball has traveled quite a bit of distance. Okay, so the idea here is this: what if I were to grab the ball's distance, let's say at t equals to, I don't know, 4.99 seconds. Let's say the ball is here. And see, in 0.01 seconds, the ball shouldn't have traveled too far away from 4.99. So in other words, let's say at t equals to 5, let's pretend that the ball is, I don't know, I'm just going to draw it over it, right? So it's basically slightly moved a little down, okay? So what do you notice? If I keep my time frames close to each other, okay, the closer I stay to 5 seconds, I'll notice that the change in speed from, let's say, 4.99 to 5 seconds won't be as much as opposed to the change in speed from 4 seconds to 5 seconds. So if I could find the average velocity continuously and get as close as I can to 5, I should see that the velocity should settle down to that number. And the number that it settles down to, that will be your instantaneous velocity. So basically, here's what I'm doing. If I take, so let's do this. So let's take actually, and let's actually write this down. So what I was just saying, we can kind of summarize it. So the goal here is, to find the velocity at t equals to 5. But we need to use two time frames. Okay. Reason being why I can't use the same time frame is because I'll be dividing by 0. Okay, so it's kind of like that tangent problem that we did earlier. So I need to use two time frames. Basically, the reason why we want to use two time frames is so we could, to be able to find the distance, right? Because if I know we have the formula for the position, so I could say this position minus the starting position, which would give me the distance I've traveled. Okay, so here's what we're going to do. So let's choose t equals 5.1. Now, why did I choose t equals 5.1? Remember, we talked about it. We want the times that I choose to be as close as it can to 5. Okay, so we could, in parentheses, say since it is fairly close to t equals to 5. Okay, so now let's find the average velocity from 5 seconds to 5.1 seconds. Okay, so here's what we could say. So the average velocity from t equals 5 to t equals 5.1 is, how do I find the distance? Remember, it's distance divided by time. So the distance would be what? The position at 5.1 minus the position at 5 divided by the time elapsed, which is 5.1 minus 5. Remember, S, by definition, just to recall your memory, S of t was what? It was negative 4.9 t squared. So basically, what am I saying? Plug in 5.1 for t, solve it out, minus plug in 5 for t, and then this is the elapsed time, which is t2 minus t1, so 5.1 minus 5. So this gives me 4.9 times 5.1 squared minus 4.9 times 5 squared all over 0.1. And if you simplify that, you get 49.49. And you get a negative number, which is fine because it's going downwards. Okay, so that's meters per second. Okay, now here's the thing. Could I say, oh, this is my instantaneous velocity at 5 seconds? And the answer is no. Because look, this is still not average velocity. This is saying on average, from 5 to 5.1 seconds, the object is traveling about 49.49 meters per second downward. Okay, but do I expect my actual velocity, instantaneous velocity, to be close to this? The answer is yes. But how do I get a better approximation, or how do I get a better approximation of what my instantaneous velocity is at 5 seconds? So take a minute and think about that. How could I get even closer to the velocity at 5 seconds? And by now, if you've thought about it, the answer is, well, pick a time frame that's even closer to 5. Because remember, the closer your second time is to 5, the closer we'll get to the actual velocity at 5 seconds. So here's what we're going to do. We can say, look, but we still want the velocity at t equals to 5. We don't want average, not average, right? We don't care for the average velocity. So here's what we're going to do. Instead of taking the time from 5 to 5.1, why don't we make it even closer? Why don't we say, so the average velocity from, let's say, instead of 5 to 5.1, we'll go from t equals 5 to t equals 5.01. And I'm going to go ahead and just give you the average velocity. The way you'd find this average velocity is just the same way that we did this. So if you want to take your time and see, if you can get that, you can do that. But I'm just going to go ahead and give you what the average velocity is negative 49.049 meters per second. And so what do you notice here? This actually, from here to here, we already start seeing what's happening. This actually got closer to what? 49. So just to be safe, what could I do? What could I do to be even safer? So we could already see that our guess is going to be what? The instantaneous velocity at 5 is negative 49 meters per second. But what could I do to be even more certain? And I'm sure by now you've guessed it. I want to pick a time frame that's even closer to 5. So let's do that. What if we do this? We say, okay, how about we find the average velocity from t equals 5 to t equals 5.001, which notice how there's barely a time difference between these two. If you do that, you're going to get is negative 49.0049 meters per second, which means I got even closer to negative 49. So here's what we could do. We can now make a conclusion and say, well, and by the way, without doing the math, you could probably guess. What's the average velocity from t equals 5 to t equals 5.0001? If you were to guess, it would be the same thing as this, except you'd have an extra 0 here, which means we got even closer to 49. So here's what we could say. Thus, the instantaneous velocity is v equals to negative 49 meters per second. Okay, so in fact, what are we saying? At exactly t equals 5 seconds, at that one instant, so it's kind of like coming back to this, we drop the ball. At 5 seconds, at that moment, this ball has a velocity of 49 meters per second. Now remember, why is it negative? Because it's going downward. Okay, so remember, we start with the average velocity and we get the time frame, or we make the time frame smaller and smaller and smaller. And what is it that I'm doing? I was making the time frame smaller, but which time was staying fixed? T equals 5 was fixed. How come? Because I wanted the velocity at 5 seconds. Okay, so you might have a question, well, did I have to start with 5.1 up here? Or could I have started at, let's say, 4.9? And the answer is you could have started from 4.9. Okay, it doesn't matter. So as long as you kind of start away from the value of interest and then you kind of start making your way towards the value of interest, and then your numbers, your calculations that you're making, they should get closer and closer to the value that you're interested in. Okay, and that's how you find instantaneous velocity. So for homework, you're mainly just finding instantaneous velocity and slopes of tangents and equations of tangents. So I think the two examples I did here pretty much wraps up everything you do for this section. So we will discuss these in greater detail within this chapter. We're going to come up with other ways of doing this, and in fact, we haven't talked about an idea from calculus, which I'm sure you saw it in analysis, but we're indirectly talking about limits. So if you remember what limits are, then you know exactly what I'm talking about. If you never have seen limits, don't worry about it, because we're going to talk about them as if you've never heard of them before. Okay, but that basically wraps up section 1. And please feel free to ask me questions if you have any on any part of the notes in class. Okay, take care.